Okay, the first of our categories is atmospheric and surface measurements. Now, before we go through all of these, I'm going to go through these pretty quick. The video has been really long so far. I apologize, but this is important stuff, so I want to get this out to you. I want to tell you all this. I'm going to go through this as quickly as I can, and you can pause it and go over things again if you need to. So, basically, there are two types of measurements for atmospheric and surface. For surface only, you can look at soil mechanics and hardness, penetrability, stuff like that. We'll talk about that if you want to do that. But for atmosphere and surface measurements, you're looking at properties and composition, basically. So what is a property? A property is a quality of the atmosphere or the surface. Pressure, temperature, density, viscosity, charge, pH, wind speed, humidity, stuff like that. You know, most of these are associated with the atmosphere, but they work for surface as well. Composition are the constituents of what you're looking at. Constituents of the atmosphere or the constituents of the surface. What are the elements? Basically, that means what are the elements that are in there. Sometimes you'll look at compounds or ions or salts, or if you look for biologicals, that's a specialized thing. You can look for amino acids type deal. Acids, bases, minerals, metals. Those are the kind of things you can look for with when you look for composition. Those the constituents. What makes up this soil? What makes up this ice? Or what makes up this atmosphere? That's what you're looking for with composition. So I'm going to go through different properties really quickly, and then the instrument that's used to measure those properties, and then you can go from there. What you want to do is quite simply, if you find a measurement you want to measure, if you want to measure pressure, you use a pressure transducer or pressure probe. Google it, look it up online, look it up on Wikipedia. Some teachers don't like Wikipedia, but it's a great place to start. I wouldn't use it to cite something, but usually they have 20 or 30 references at the bottom that will take you to the places you need to go to find all the information you need. So Google these things. All the information's out there. You can find it. You just got to look for it just a little bit. Okay. So properties. Pressure is a big property. It's measured by a pressure transducer. Really, it's a touchy measurement, meaning that the pressure transducer has to touch the atmosphere or whatever it's measuring. Okay, that's a big deal. We'll talk about that in a second. Temperature. Use a thermocouple. We're going to talk in detail about temperature in the temperature section, so I won't talk about it right now. Density, it's a combination. Density is mass divided by volume. So you have to measure mass and volume in order to get density. It's not a direct measurement. It's a measurement of two different things to calculate density. Viscosity, you use viscometers or rheometers, and you can also measure it indirectly. The classic experiment in a lab is dropping marbles or ball bearings or whatever into a vat with different liquids in it and seeing how fast it falls. That tells you the viscosity of different liquids. So you can measure it directly or indirectly. Indirectly is usually easier to measure for stuff that we're doing. Charge, electrometer or galvanometer. Again, it's a touchy measurement. You have to actually touch. You have to measure the charge. You'll build up a charge. It's a potential that you're looking at with that. pH stands for percent hydrogen. It's electrode, a pH meter indicator. You'll know if you've ever worked on a pool or something, you know what a pH meter is. Again, you have to touch the fluid in order to measure the pH of it. You're determining whether it's acidic or basic, stuff like that. You can accomplish some of this can be accomplished if you want to look at the properties of the composition of whatever you're looking at as well. You can determine you can be more complete with that information. pH is sort of if you don't have much mass left, you can use pH to cheat sometimes. Wind speed, the classic way to look at wind speed, like on all these storm chaser vans and stuff, these little things that spin around on top of the van, those are called anemometers. That's the direct measurement of wind speed, but that requires something to be sitting still. If you're moving, most of your probes will be moving. If you're flying through an atmosphere, you can't use an anemometer because you don't know what is because of your speed and what is because of the actual wind speed. There might be ways around it, but you could. So what I'm getting at is there's indirect ways to measure velocity through accelerations. You can use an accelerometer to do that. This wind speed can be inferred through the changes in acceleration of your probe. And humidity is is a hygrometer, and but humidity typically requires other measurements like temperature, pressure, and is usually a mass measurement as well. Composition. To measure composition, you're looking at a mass spectrometer, really. And a mass spectrometer is an analytical technique that measures the mass to charge ratio of charged particles. I'll talk more about this in a second. Used for determining the mass of particles, elemental composition, that's what we use it for mainly, elemental composition. What are the constituents of this soil, or what are the constituents of this atmosphere? Is it hydrogen? Is it oxygen? Does it have carbon in it? Does it have nitrogen or whatever? You know, that's what we're looking for mainly, is elemental composition of a sample or molecule, and the chemical structure. The way it works, it ionizes chemical compounds to generate charged molecules, and these fragments are measured with their mass to charge ratio. That's what the mass to charge ratio comes from. Now, the procedure, basically, the basic procedure is as follows. You have a sample of something, okay? Whether it's a solid like a surface or an atmosphere, and you hit that sample with a laser or electron beam, something like that. It ionizes it. You don't see that part, but it happens really fast. It ionizes it, and then those ions are separated by an EM field, an electromagnetic field, and then this mass to charge ratio is measured. But what happens is it lets off a spectrum, essentially. It lets off light, a spectrometer. It lets off a spectrum, and this is measured by some sort of optical device that actually sees this event occur, and then it sees the spectrum that you know that's emitted from this reaction, and it goes, oh, it's got hydrogen, it's got oxygen, it's got nitrogen, it's got iron, you know, whatever. So it's a weird one, but it might have it. This spectrum that is created by this interaction between this laser or electron beam hitting this substance is what's actually measured. That's why it's called a spectrometer, the spectrum. So basically, laser hits something, fluoresces, light, you know, the spectrum happens, and this is read by a device that's sitting there monitoring this, an optical device monitoring this, and then it's calibrated ahead. That's how it works. The calibration is it's calibrated ahead of time, and they know what it's made of. So there's two basic types, and I'm oversimplifying this. If anyone, I'm really making this extra simple for our purposes and InSPIRESS. And these two basic types, I came up with the nomenclature myself. So this is something that I call them, me and PJ. There's an internal mass spec and an external mass spec. An external mass spec is very similar to spectroscopy, really. Internal mass spec is you get your sample and you put it in a box, and inside this box is where the laser beam hits it. It makes this spectrum, and then the spectrum is read. So it all happens inside of an enclosed area. That's why it's internal. I call it internal. All happens inside of an enclosed area. The external, the laser beam is shot away from it, like on the rovers on Mars. They do this a lot. The rovers on Mars, they tool around and they shoot a laser beam at a rock. They say, oh, that's an interesting rock. I will shoot this rock with my laser beam. They shoot the rock, and the laser beam hits the rock, and it goes, and there's this spectrum that's created, and it's read by this optical device, and they go, oh, that rock has magnesium, it's got sulfur, it's got iron. Okay, we're done. You know, that's how the external ones work. And again, oversimplified if anyone is curious, but it works for what we're doing. The internal ones, the one where it's kind of like an easy bake oven, right? So you get your sample, put it in a box, and the laser hits it. Everything happens inside of this box. Those are typically more accurate. However, you have to get the sample inside of the box somehow. And then the box and everything, it weighs a little bit more typically. So they're more accurate, but they're more difficult to use, and they weigh a little bit more. The external ones where it shoots a laser outside and it fluoresces outside, those are less accurate for obvious reasons, because there's control issues and stuff, and it's outside in the light or whatever. But they weigh less, and they're easier to use because you don't have to put it inside of a box. So there's a trade there. There's accuracy, and there's accuracy versus, you know, a more accurate, heavier, and more difficult to use device versus a lighter, less accurate, and easier to use device. So you can decide which one you want to use later. So properties and composition. The issues with properties and composition, I called a lot of these measurements, they were touchy measurements, which means that the probe the temperature sensor or the pressure transducer, the temperature sensor is called a thermocouple. They have to actually touch whatever they're measuring. If you want to measure the temperature of me, I have to touch me with, like, I've got those those things you scrape across the forehead, you know, they're great for the kids. So I have to touch my forehead with that temporal scanner, right? They've got those laser beam ones, but those don't work as well, and those are a very limited range. Thermocouples are touch. You got to touch something in order to measure the temperature of it. Pressure is the same way. Most of them are that way. So that's an issue because when you start designing your payload, you have to allow for, oh gosh, this pressure transducer has to have a hole in it so it can see the atmosphere, so we can measure the pressure of the atmosphere. So we got to put a hole in our probe. Whoa, that's a big deal. When you start thinking about that, it becomes a big deal. Some properties can be inferred, measured indirectly, viscosity and wind speed. They're measured through accelerations, how fast or slowly it goes through something, or if it changes directions, you can measure wind speed that way. Spectrometers are not robust. There's a laser, there's some sort of optical device that observes the laser hitting the thing, you know, so they're not robust. They're not robust. They can't handle, you couldn't throw them out of a plane on the ground and hit the ground and expect them to survive, you know, that they're not robust. Hopefully we've come to your class already. If we haven't, we will. We'll talk to you about the LCROSS mission, which was a NASA mission to our moon, and where they used a mass spectrometer to look at samples on the moon, and how they used how the LCROSS mission worked, how they got around some of the issues of spectrometers not being robust. How did they do that? How did they work that issue? If we've already been in your class, then you know. If we haven't, then you'll find out. So there's a trade, internal versus external, again, like I talked about earlier. There's a trade there with accuracy versus ease of use and stuff like that, and mass. Okay, internal structure and tectonics. Internal structure is a weird one. It's one of the ones, when you say you're going to measure temperature, you measure temperature, right? Internal structure, when you say, I want to measure the internal, I want to look at the internal structure of a planet. There's no such thing as an internal structometer, an internal structurometer. Those don't exist. The way you measure the way you determine internal structure is through vibrations, seismic events, or tidal heating, where the surface is being squished, you know. Basically, essentially vibrations, movements of the surface. That's how you determine internal structure. So internal structure of a planet can be imaged, constructed using seismic information from quakes or vibrations from the planet. Essentially, you're measuring the vibrations. Like, even if it's a big impact, it sends vibrations through the whole planet. That's what, when an earthquake happens, it sends vibrations through the entire planet. We'll talk about how that works in a second. But tectonics describes the large-scale motion of the plates. Again, very slow, long-term stuff, tectonics. But we're going to be in Enceladus for a while, so you might be able to observe some of this. And again, that's an interesting one because it's very rare to be at a planet for so long that you can observe, that you have time to observe tectonics shifting. So check with your UAH team to see how long their mission is on the surface. The Rhea and Dione flybys, you could look at tectonics there. They're going to last for years, like 2 or 3 years. So again, check with the UH team on that one. So how do seismic waves image the planet's interior? So three-dimensional images of a planet's interior can be generated by using two-dimensional information. And you can basically, you use the quakes and tidal heating, the stuff that moves the planet itself, the vibrations that go through the planet, you use those vibrations. So you generate three-dimensional images by stacking 2D images on top of each other, okay? It's just like a CAT scan. If you've ever had a CAT scan, what a CAT scan does is it has one source, the film, okay, that sits there. And then the X-ray goes around and images it at different angles. So it has one source, and the sensor and it has one receiver, and the energy source moves around, okay? And takes different images, and then those images are stacked together in a computer, and you get a 3D image. Basically, you're taking slices of it, you stack those slices together, and eventually you get a 3D image of what you're looking at. That's how CAT scans work. Your energy source moves, and your signal receiver stays the same, or doesn't move. It's the film that just sits there. With internal structure, it's the opposite. Your energy source, you have one energy source, the quake. It just sits there and it makes a big vibration that sends it through the whole planet. But we have several, the receivers, they don't move, we just have a lot of them, okay? So what happens is there's a quake that occurs in the planet, and it sends vibrations throughout the entire planet. And you have sensors all along the planet that measure the vibrations from this quake. And from those measurements, we can get a picture of the inside of the planet. It's really kind of cool. So the more receivers you have, the more receivers on the planet, the more sensors you have like around the planet to sense this seismic event, the better, obviously. So this is the Earth. Don't let this fool you. This is not Enceladus. But so seismic waves happen. There's P waves and there's S waves. P waves are compression waves. S waves are shear waves. If there's an event, there's an earthquake here, it travels through, and there's a time difference. And basically, as the waves travel through the planet, if there's sensors all along the planet, you can get an image, you can get an idea of what the planet looks like, essentially. Because the waves, as they travel through different materials, the waves themselves change. And so the sensor right here measures different waves than the sensor right here. It measures different kinds, it measures different, the amplitude changes, the time scale changes that it took to get there. All that stuff changes, and so they can stack that information together and form an internal image of the planet. This is what is this? This is our moon? Yeah, this is our moon, I think. Earth's moon. Again, this is Earth. So we have our inner core, our outer core, then our mantle and our crust. And so an earthquake happens. It sends waves through the entire planet. There's P and S waves. You'll notice that the S waves can't travel through a liquid. Shear waves can't travel through a liquid. So right here, there's no shear waves at all, no S waves. And here's a dead zone because the P waves are deflected. So don't worry about these details, essentially, but just know that in order for this to happen, you have to have a seismic event, and these things do occur on Enceladus. They have quakes. And then there's constantly vibrations going on because of the tiger stripes are shaking the planet and sending out these huge cryovolcanoes. Basically, the whole planet's kind of vibrating, and so and you need sensors along the entire planet. Okay, that's the hard part, is the sensors all over the planet, and it's three-dimensional. So you want them around it this way, then this way, So sensors all over the place. So how does the seismometer work? So we're looking at seismic stuff. You heard of seismometers, right? Basically, this is a really old school seismometer, very old school. It's just a spring mass system. So the seismometer itself, it's tied to the ground, right? It's boom, it's there. So if the ground shakes, the seismometer will shake, right? And then it's held by a spring. There's a mass held by a spring, and so when the whole thing starts to shake, this shakes, and this thing kind of stays stationary. You've seen this before, right? You've seen it on TV and stuff, whatever. This is very old school, simplified. They're not made this way anymore. They're most digital now. But so as this thing goes up and down and this thing rolls, the rolling paper, it measures the scribbles on the piece of paper, and they go, oh my gosh, it's a 10.4. And so as the wave passes, the suspended weight initially remains the stationary, and then so that's how they measure it. And then the spring, they call it, they quote spring because they're not really springs anymore, are optimized for a specific frequency. So if they expect to have certain waves in some area, then they'll optimize that spring. That's how seismometers work. Accelerometers are very similar to seismometers, except accelerometers will measure when there's no movement, because they measure accelerations and they measure gravity, stuff like that, local accelerations. They'll measure local gravity if they're just sitting still. There's an accelerometer inside your phone, or most smartphones, an accelerometer, and there's apps you can get to access the data. You can put it down and it'll measure 1G, going in that direction. So that's an accelerometer. Seismometer won't measure when there's nothing going on. So it measures accelerations. That's why it's called an accelerometer, as the name would suggest. And acceleration is just a change in velocity, basically. So, this is an acceleration. This, whatever, rotating or even just kind of speeding up. That's an acceleration. So it measures changes in velocities or motions, movements, vibrations. Behaves like a damped mass on a spring, just like a seismometer. Commercial devices, the accelerometers that are used commercially, like in iPhones and whatnot, piezoelectric, piezo-resistive, and capacitive components. You can look them up. I can't tell you which one's better or which one's worse for your application. We'll have to think about that later. Relative position can be calculated, integrated from accelerometer data also. If you know, basically, if you have an accelerometer, like in this phone, if I were to throw my phone, I'm not going to do it. If I were to throw my phone to someone over there, they were to catch it, and we were to access the accelerometer data, we could determine how far it went and the flight path that it took, or not the flight path, but the distance that it went. And if we know where it started from, if it started from me, then we could determine it'll be able to tell us that it went that direction and it went that far in that direction until it stopped. And so basically, you can use accelerometer data to determine relative locations. So if you have a known point and then something is released from a known point, like for instance, if you have a spacecraft and then something is released from a spacecraft, and then it just sits there and it goes through accelerations, it's being pulled toward a planet, and it falls, then it hits the ground, and it might do this or something, then it comes to a rest, right? It comes to rest. But if you have the accelerometer data from this probe, you can back calculate, and if you know where it started from, you can determine where it ended up on the surface of the planet. That's actually very interesting and very helpful, okay? Because all these instruments, all these measurements we talked about so far, temperature, pressure, all those measurements are great, but if you don't know where they're taken, if you say the temperature on Enceladus is 4, that doesn't tell us anything. Where is it for? We want to know where and when, okay? So we need time and location data as well. And that's how an accelerometer can help you also. I know we're talking about internal structure right now because an accelerometer will feel the vibrations just like a seismometer will. But an accelerometer can also give you position data based on the acceleration data. It's just a numerical integration. You don't have to know calculus for this to work. You don't have to know how this works. It's actually difficult. Numerical integration is quite difficult. But just know that there is a relationship between acceleration, velocity, and position. And that if you start at a known position, and the spacecraft will know its position. It'll know where it is in X, Y, Z in space, okay? It knows where it is, and then it releases you, and you start collecting data, on your accelerometer. Then where it ends, where it lands, you'll be able to calculate where that was exactly on the planet, or where, and all the way through. If it takes measurements the way down, you can also determine where these measurements were taken along the way. Does this make sense? Any questions? Good. Okay. There's no one in the room. Just so this is important. Accelerometers are important not just for internal structure. They're very important for internal structure because you can use them to, act like seismometers, and they're really small and cheap, much smaller and cheaper and more robust than seismometers. But you can also determine position data using an accelerometer. That's important. So, issues with internal structure. With each of these categories, we're going to go over some issues. And so, internal structure, you got to have a network. That's the biggest thing. Is there's a network of sensors you have to lay out on across the planet. And as the general rule of thumb, is that the sensors can see as deep as they are far apart. So if they're 100 meters apart, if you have three sensors in a triangle, 100 meters apart, they can only see 100 meters deep. Okay, if you want to determine the internal structure of a planet, you got to be sort of across the planet from each other, right? You got to be really far away. That's an issue because the lander's only landing in one location. So that kind of implies that you're going to fall from orbit, at least at a couple more locations. So you need at least 3 sensors to form a network. That's the bare minimum is 3. You want to probably have more. You want to be far apart in order for them to see deep. They have to have the same internal clock, which means they have to synchronize their watches. And then, so all the sensors are in the spacecraft. They go, ready, go, and then they jump out. Okay, so because if one of them feels a vibration, then another one does, and their internal clocks aren't the same, then who cares? The data's meaningless at that point. So you also want good contact with the surface. That means that if the surface shakes, you want the accelerometer to shake. You don't want to put the accelerometer or the seismometer, you don't want to put the whole thing inside of a big spring system so that, yeah, it absorbs a really cushiony fall or something, but then once the ground shakes, this thing just kind of stays stationary, right? You know, when the ground shakes, you want this, you want your probe to shake too, okay? So, impact resistance seismometers are not robust. Springs and masses and stuff, they're not known to be robust. Accelerometers actually are robust. Seismometers are more sensitive. They're usually more accurate than accelerometers. So there's your trade. You got accuracy of a seismometer, but you got the accuracy. The accuracy is given to the seismometer. They're much more accurate, but an accelerometer is much more robust. An accelerometer, we put them on missiles, on bunker busters and stuff. So they can thousands and thousands of Gs. Accelerometers can tolerate. You know, accelerometers, and you can take a phone and they'll measure the. I'm not going to do it. I'm not going to throw mine. I've broken my phone enough. So but accelerometers are pretty robust. So they'll withstand thousands of Gs easy. Accelerometers can be used to calculate position, which is nice. Seismometers not. Orientation on the surface. Sometimes orientation is important. It depends on what you're using. A seismometer or accelerometer. If it lands this way, whoa, almost dropped it. If it lands this way or this way or this way, how does it have to land for it to work right? They have 3-axis accelerometers that'll work no matter how they land. And the accelerometer in a phone is a 3-axis accelerometer, so that's how you can play those video games. What's that? Cube Racer. I'm terrible at it, but my niece is awesome. She can but so that's why you can do this. It's a 3-axis accelerometer. It knows which way it's facing. So now, if you come down with the lander and you're ejected off the lander, 100 meters is the minimum distance you need to be away. The lander is actually noisy, creates lots of vibrations, and the seismometer or the accelerometer will sense those vibrations. How long do you operate your network? How long can you operate? And then you got power communications, thermal structural issues, all those the standard issues there. So creating a seismic network, basically, since the lander is at a single point, and so we have to create a network. We want the network to be far apart, right? I'm going to go ahead and assume that we're going to have to drop some of these probes from orbit. Okay, so there are two options from falling from orbit. You can either go deep and just penetrate into the surface, and so you'll penetrate in the surface, or you can skip across the surface, right? It kind of makes sense, right? If you fall from orbit, you're going to get stuck into the ground, or you're going to skip across the ground. And you can design it that you'll do either one of the, you can design it, you can kind of, not design it to ensure it, but you can help to ensure that it goes one way as opposed to the other. So penetrating the surface, there's pros and cons to each. The positives, you get a much better connection to the ground. If the ground shakes, you will shake. There's radiation shielding when you're below the surface, and there's more certainty with your position. You hit the ground, you're going to be there. Negatives, really high impact load. It's all about stopping distance. If you penetrate the ground and go 10 meters deep, then you went from going very fast to 0 meters per second within 10 meters. That's a lot of deceleration. Just like when you're in your car, you're driving, and this, I'm going to make the light, I'm going to make the light, I'm not going to make the light. Hit the brakes. All the cans in the McDonald's from the back of the car end up in front of the, end up in front. That's a really short distance, short stopping distance, high decelerations, right? That's what your probe will feel also. All the McDonald's in the back of the probe is going to be shifted to the front of the probe. So impact angle is an issue. There might be some communications issues if you get too deep in the surface. And then also when you're surrounded by ice, you're going to get colder quicker, okay? If you're sitting on the surface, you only got ice on one part of you, okay? But if there's ice all around you and you're down below the surface, it's going to be really cold. That's just bear that in mind. Okay, so if you're on top of the surface, you're going to have lower impact loads because you'll slow down over like 100 meters as opposed to 10 meters. Less heat is conducted away because you're not fully encapsulated in ice, and then probably better communication because you're on the surface. When you're on the surface, just sitting on the surface, you have poor connection with the ground. poor connection with the ground. There's a possibility that the ground might shake and you won't. The possibility exists. Less position certainty. When you hit the ground, you'll skip around. You might not know where you're going to end up exactly. When you hit the ground and you stick in the ground, you're going to stay there and you know where you're going to hit. So, and then there's surface features to contend with, big rocks, stuff like that you might run into, or something that gets in your way for communications. And then you're exposed on the surface, more radiation. Here's a really nice drawing. I'm going to go ahead and close this window a little bit without stopping. Sorry, I'm blind. So here's a really nice drawing of internal structures that when you penetrate the surface, basically you drop and you stop right there, and you're stuck in the ground. When you're right on the surface, you get dropped and then you bounce, and you don't bounce like that. This is not very well drawn, but you just kind of you slow down over a longer distance. That's basically what that's trying to show you. It's pretty good. I drew that. Don't make fun. So that's it for internal structure. We'll talk more about this. If you have any questions, just feel free to ask when I'm there, or send me an email, something like that. But or rewatch that section if you have any questions. Heat flow and temperature. Temperature and heat flow. They're different science objectives, but you're doing sort of the same stuff, and we'll talk about that. So temperature measurements, the objective is to understand the thermal environment on the surface of Enceladus. Temperature measurements are sort of the whole planet, okay? You want to measure large, it's the big picture type stuff, okay? Usually at many points along the surface. So you just think about measuring temperature all along the surface, of the United States or something. That's what you're looking at here. Like for example, what are the tiger stripes like compared to other areas? You can measure temperature around the tiger stripes versus temperature at the North Pole, something like that. Heat flow is more precise. It's more measurements. It's the objective to understand the thermal environment. Basically with heat flow, you want to understand the thermal environment inside of Enceladus. The temperature measurement is a network on the surface. Heat flow is you want to see how the temperature changes as you go deeper down into Enceladus. That's the difference. So usually you have one or maybe two if you're really good. Probably just one though. Point where you measure temperature and you go down deep. Okay, we'll talk about this more in a sec. So for a given area, temperature is a single surface measurement, while heat flow are multiple measurements on the surface going down to a certain depth. Okay. That's the difference. Temperature is surface measurement, but it's usually spread over a large area, many different surface measurements over a large area. Heat flow is one point basically, but you're measuring the temperature going down through the surface, going down from the surface to a specific depth. That's heat flow, because the temperature should change. Okay. Temperature network provides better measurement over entire planet. It's a big picture measurement. Heat flow is a temperature profile, basically. How does the temperature change for one single location? How does it change from the surface as you go deeper into down in the surface, like 10 meters or whatever? How does the temperature change? Maybe two locations if you're lucky. Both measurements use basically the same instruments. Thermocouples are what we're going to use. So temperature network. Scientists suspect that the North Pole, like I said earlier, the North Pole is the South Pole is warmer than the rest of the planet. That's why that's red down here and it's yellow down here. They think the South Pole is warmer than the North Pole, but they don't know how the temperature changes. They just think the South Pole is warmer. They don't know if it's a gradual change or if it it's the same temperature till you get to the equator and then it changes. They don't know. They don't have a clue. Okay, so that would be really interesting. Is first of all, what are the actual temperatures? Second of all, how does the temperature change? Does it change gradually as you go all the way up? Is it a constant change? Or is the temperature constant from here to there and then it changes? Something like that. We don't know. But that's interesting stuff you could look at. Is there a variation in the temperature in different regions of the South Pole? Is it very, very hot here and then it cools down, or is it all the same temperature around here? These are things you could look at. Really interesting stuff. And how wide is the high temperature region? So is it just there at the South Pole? Is it a quarter of the planet? Is it a half of the planet? What is it? So that's temperature measurement, planet-wide stuff. Temperature network. Temperature network. The probes reside on the surface. You're basically dropping a bunch of probes on the surface of the planet. The network of probes implies they need to be dispersed. The farther apart, the better, and the more, the better. Okay, this is just like internal structure. The more and the farther apart, the better. This implies that some will probably have to fall from orbit, okay? Because one lander, one location. If you want to have a network over the whole planet, you got to drop some from orbit, right? So this implies that some will probably have to fall from orbit, and then so that implies that you're going to have high impacts on the surface and high forces, stuff like that. Final position where the measurements are taken are important. But if you're going to drop from orbit, there's more uncertainty with that position. I mean, you could bounce a kilometer or two down range. You know, that's a you know, it's not that big compared to a planet, but you want to determine how accurate your position measurements are going to be. So heat flow. That was temperature. Again, planet-wide stuff, surface type measurements. Heat flow. Scientists believe the core of Enceladus is warmer, okay? Especially near the South Pole. How does the temperature change with depth? They don't know how it changes with depth. Does the temperature level off or continue to decrease? They did this measurement on the moon. On the moon, you've probably seen the videos. Actually, you probably have. There's the astronauts on the moon. They drove these spikes into the moon, and they would jump on them and jump because they were basically these temperature probes. They were 3, 4, 5 meters long. I can't remember exactly. And they measured, but they had to drive them in the ground. They had to get them straight too. So they had astronauts do them. We don't have astronauts on Enceladus, or even trained monkeys or gerbils or anything. That's what's hard. What they found on the moon, by the way, is that once you get to a certain depth, the temperature kind of stays the same. Like on Earth in caves, it's like always like 65 degrees or something. Once you get to a certain depth on the moon, and it's not that deep, it's a little bit less than a meter actually, then once you get to a certain depth on the moon, temperature stays the constant. So if we ever go back and build a moon base, throw moon dirt on top of it and we're good to go, basically is what that amounts to. For this, we're not going to build an Enceladus base, probably not, at least not in our lifetime. But they want to know how the temperature changes as you go down. This is my drawing, by the way, cold and warm. So that's kind of what you do, is it's a profile. You measure the surface and you measure periodically. You measure distance apart, right? And you go to a certain depth. You go as deep as you can go, really. The deeper the better. But you got to know these deltas. You got to know how far apart these temperature measurements are, or it does you no good. So the profile from the surface to a certain depth. And that certain depth is as deep as you can make it, but you'll have to figure out how deep you can go. Measure the temperature at specific intervals. So that's what these T's are. That's specific intervals. And overall accuracy depends on the overall accuracy of the heat flow measurement depends on the temperature and position measurements. So how accurate this individual thermocouple is, and then how accurate your positions are. And how many you have. That gives you finer resolution too. And watch out for thermal shorts. A thermal short, just like electrical short, like he created a short in the electrical circuit or whatever. That's when you just take a wire and jump it across two things. A thermal short is the same thing. So basically, if you have a long tube or a long pole or something, if you make it out of metal, then all the heat from down here will conduct through the metal pole all the way to the top. So your metal pole will be the same temperature eventually, right? That's a thermal short. When you use something that conducts heat from one point to the other, that's a thermal short. You want to watch out for that when you're taking thermal measurements because it'll give you bad measurements. So watch out for thermal shorts, basically. It's just like an electrical short. So heat flow, the temperature measurements at the surface to a depth, and then along the way at certain intervals. The deeper the better. The more intervals you have, the better. The distance between each temperature measurement must be known. You have to know, like from this measurement to this measurement, you got to know that, okay? Absolute depth is desirable. So let's go back one. So this distance, you have to know this distance, right? This distance, this distance, this distance. You have to know those. You don't always have to know how deep this is compared to the surface, okay? True, if you have a surface measurement and then you have intervals, you should be able to calculate that. But sometimes you won't get all that information. It's more valuable to know this interval distance and then the distance and the different temperatures between those intervals than it is to know how deep it is below the surface. Okay, we'll talk more about that later. So, but absolute depth is desirable. It would be very helpful, but it's not as important as the difference, the interval distance. Getting the depth, getting to a depth requires energy, and there's a few basic methods for that energy. So you have to get to a certain depth with heat flow, right? You have to get to, let's call it 5 meters. Let's say 5 or 10 meters. That's just making stuff up, okay? That's a long way, 5, 10 meters. That's like 15 feet or 30 feet. 30, you know. So anyway, like 3 stories at 10 meters. So how do you achieve depth? How do you achieve depth? We're going to give you these hints because it's tough to do otherwise. There's 3 basic ways to do it. The first one, the DLR mole. DLR is the German NASA. It's the German aerospace branch of the government. It stands for Deutsche Luft- und Raumschaft, basically. German air and space, basically, is what that stands for. They have something they call the mole. It's a miniature self-contained pile driver. You know what a pile driver is like when you've ever seen them make a bridge or something. They pull a mass up and they drop it. They pull a mass up and they drop it. They pull a mass up and they drop it. That's a pile driver. It's driving piles. And so this mole, basically, it's about this size, a little bit bigger than a pen or a marker, you know. And inside of it, there's a little mass, and the mass goes up and down, goes up, slowly up, down, slowly up and down. And eventually, after a long period of time, it makes its way down down into the, you know, it kind of digs its way down. And then along the way, it's letting go of a little tail. It's got a little tail that has temperature sensors on it, okay? It's small, cheap, low mass. It was designed for heat flow experiments on Mars. They're going to use it, the NASA InSight missions going to Mars. They're going to use the DLR mole for that. It's now called the DLR HP3. No idea what HP3 stands for. But the mole changed names to HP3. We used to call it the mole back in the day. I still call it the mole. But I think they call it HP3 now. Google it. It's out there. NASA InSight mission is the newest mission where they're going to use it. The negatives: will it work on Enceladus? It was designed for Mars and even modified for the Moon sometimes. Much warmer than Enceladus. Can it work there? Can it reach the required depth? I don't know. And it's very slow. Just imagine. Doot, 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 doot. I mean, it's very slow. I mean, do we have enough time for this thing to work its way down? And then what happens if something hard gets in the way? It just kind of digs it around it. But how does it? Is it going to measure it? You know, is it going to work? We don't know. So the next method, drill. Basic stuff, right? You know, Bruce Willis, Armageddon, let's just drill it, raw. You know, drill down, make a nice hole, put temperature sensors in it, boom, right? So that's another method to get your achieved depth for heat flow experiments. Now drill is going to give you the most precise hole, okay? It'll most likely reach your depth. Depending on how deep you want to go, a drill can achieve it. It's accurate, precise, straight hole. It's if you had all the mass in the world to do it, drill's the way to do it. Or if you had humans to do it, drill's the way to do it. They're big. The negatives, they're big. They're power hungry. They have really high mass. A drill requires a normal force. You ever watch someone drill something and they don't hold it really hard and it kicks their hand back? Because you got to hold it steady, because once you get to a certain depth, there's the force of the friction that the drill bit has on just the surrounding material is going to kick back the thing that's holding it, right? You understand what I'm saying? It requires a large mass just to keep the drill steady, essentially. That's why. So drills, there's a large mass just for the bit itself, and then a large mass to hold the drill in place so it doesn't move. Those are honeybee and swales. They make drills for extraterrestrial stuff. So drills in space and stuff, on the moon and stuff. The last one, penetrator. It's a kinetic energy device, basically. Whether you it turns motion energy, movement, kinetic energy, and then it digs a hole in the ground. It's like a bunker buster missile, or imagine high pressure gas using to fire into the ground, something like that. That's a penetrator, essentially. Lunar A is a mission that used penetrators. It didn't fly. It's a Japanese mission. Mars 96 didn't fly. Deep Space 2 flew, but the penetrators failed. And then Moonlight's a proposed mission to the moon that uses penetrators. None of which, we've never had a penetrator mission that was successful. But we've got lots of ideas for penetrator missions. There's no reason they shouldn't work. But just give you a heads up, never had a successful penetrator mission. NASA has, or at least the human race, as far as I know. So utilizes potential energy. It means it's requires less energy. The drill doesn't, it brings its own energy with it. That's why it's so big and heavy. It's likely to reach its desired depth. You can calculate the desired depth by physics. There's more size options. You can go real small or big or whatever, and they're very fast. It gets to the depth very quickly, much faster than the drill. The mole is like deep, 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 deep. The penetrator's like boom, depth, did it, boom, we're done. However, less location certainty than with, like how deep you're going to get. There's issues on, you might achieve your depth, you might not. You might go too deep. What happens if that's the case, High impact velocities. The high impact velocities mean you're going to have high forces, high accelerations on the inside. Can your components put up with the G's, basically? Impact angle you got to hit. If you hit too shallow, you'll just kind of go whoop and skip back out. That's bad news. That kind of defeats the purpose. And then your test area is disturbed, to say the least. You're hitting it with a projectile, your test area. So if you're going to do heat flow measurements, you're going to change your test area drastically. So you're going to have to wait a while for it to settle down. Essentially, all that energy, all that heat and friction is going to change your test area for a while. You got to let it sit for a little bit in order for it to settle down and get back to normal to where it would normally be. So, how is temperature measured? Temperature is measured with a thermocouple, and thermocouples are tiny. They can be as small as wires. They really are just wires. Thermocouples measure temperatures in spacecraft and in labs. You can use a thermometer and stuff like that at home, but we use thermocouples. Basically, a thermocouple is two dissimilar metals. It means two different metals, and they're sandwiched together. They're just slapped together. And then, so what happens when a metal is heated or cooled? Anyone? You? Yes, that's right. So there's no one here. I'm just making. So what happens when a metal is heated or cooled is they expand or contract, right? So two metals that are different expand or contract at different rates. Okay, and so they do this, and they bend against each other, and that interface where they bend against each other, that induces a voltage in the wire. Okay, so this bends and this one expands, this one contracts, or whatever. That induces a voltage in the wire here. And that voltage is read by a computer or a sensor or something, and it's calibrated ahead of time, and boom, you got your temperature. That's how thermocouples work. Very simple, very reliable. Very low mass. It is just a wire. Literally, it's a wire. They can be long and metal if you want them to be, but they can be as small as a wire. Okay, they don't require power to work. They actually create a little bit of their own power, but they don't require power. But you do require power to run your computer or whatever you're running to monitor the temperature. So the thermocouple itself doesn't require power, but the thing that monitors it does. That's a thermocouple. They're great, and you can weave them into. They're so small you can weave them into things. You can embed them in things. So it's great. Issues with temperature and heat flow measurements. Good contact is always an issue. If you're measuring the temperature of the surface, if you want to measure the temperature of this white coat, and you get into an area where you're sitting on top right here, and you're not touching the white coat very well, you're not going to get a very good measurement. Okay, temperature measurement is a touchy measurement. So that's why with heat flow too. When you bore down, when you get to the depth, you have to have good contact with the soil or with the ice or whatever in order to take those measurements. Contact is a really important thing with temperature measurements. If you don't have good contact, you won't have a good measurement. Again, like any measurement, time and location are very important, especially with heat flow, because there's a measurement. If the temperature changes over time, you want to know how these sensors change over time too, okay? And so they have to have the same internal clock. They have to synchronize their watches when they first start. And you also have to know the location. You can't say it's 10 degrees on Enceladus. It doesn't work. You have to say it's 10 degrees at this point on Enceladus. And then if you're doing a temperature measurement across the whole planet, you have to be able to map the temperature reading of each of them to a certain location so you can get a good picture of it, okay? And then getting away. The lander will influence the measurements if you're too close to the lander. Just like with internal structure, the lander is loud and noisy. The lander is going to emit some heat, so it's going to change your measurement, or it's going to cast a shadow or something. So the lander will impede your measurement, so you got to get away from it. And then find a thermocouple that fits the temperature you expect to measure. Those temporal thermometers that I use to measure my kid's temperature, or the one you put in your mouth when you go to the when you go to the nurse when you're feeling sick in class or something. Those are really awesome at measuring temperatures between about 80 degrees Fahrenheit and about 120 degrees Fahrenheit, because outside of that you're dead and they don't care. So they're not so great at measuring the temperature when you're cooking a turkey or something, because they're not supposed to measure temperatures above that. You know, they're not supposed to measure temperatures in the 300 degrees Fahrenheit range. They're not made for that. So you want to first find what temperature do we think we're going to see at this location, and then you find a thermocouple that works at that temperature. You know, there will be some thermocouples that work over a wide range, but their resolution is terrible, like plus or minus 5 degrees. And there are some thermocouples that work over a really small range, and their resolution might be plus or minus, 0.005 degrees. You know, so there's you got to be reasonable. You know, I mean, you want to get one that works like here, so that you don't. So if you're outside the range, you don't get. It's like, oh, we're messed up. We got outside the range. You know, so you can get some that. That means you can get some wide range ones, some narrow ones, stuff like that. So, but thermocouples are calibrated to work in certain temperature regimes, basically. And watch out for thermal shorts again. Thermal shorts are going to get you. So radiation and magnetic field. Radiation. We've all heard of it. Not everyone knows. Most people don't know what it is, really. It's energetic particles that travel through a vacuum or through matter that is not required for their propagation. That's kind of weird, not required for their propagation. So like sound waves, the waves that I'm speaking that hit this microphone, those require air or something. Sorry, my phone's going off. Those require air. They require a medium to propagate. You can't. I can't speak in a vacuum. I can't speak in space. There's in space, no one can hear you scream. I don't know if y'all seen Aliens, but anyway. So that's why sound waves are not radiation. They require that medium to propagate. But like heat, radiative heat does not require. Conductive heat requires a medium to propagate, but radiative heat does not require it. Does not require a medium to propagate. So it's particles, energetic particles that pass through a vacuum or through matter that it doesn't need to propagate. So it just pass right through it. So there's two main types of radiation: non-ionizing radiation, like radio waves, heat, radiative heat, stuff like that, etc. Those are the kind of radiation that we don't care about. Typically, radio waves are what we used to talk, like cell phone radio waves, stuff like that. That's why you don't get cancer from your cell phone. But ionizing radiation, that's the bad stuff. Alpha, beta, gamma particles, X-rays, stuff like that. Those are the really high energy particles, the ones that cause cancer, the ones that everyone's worried about. Ionizing radiation are the bad stuff. Ionizing radiation has enough energy to ionize atoms. That's what's bad about it. Basically, really fast-moving, high energetic particles will hit, and they'll hit an atom and knock an electron off of an outer shell, and it'll ionize that atom. That's why it just causes things to screw up. That's what radiation does. There's alpha, beta, gamma, cosmic, and X-ray are the ionizing. That's the bad stuff. Oh, cool. Is that the right? So Saturn radiation. Saturn has a rather strong source of low frequency radiation called the Saturn kilometric radiation, SKR, and it's traditionally used to determine the rotation period of the interior fluids in a planet. But on Saturn it won't work. And why is that? You can look at that up. You can look that up. That could be a science question. Looking at the SKR, why can't we use SKR on Saturn to determine how fast the fluids rotate on the inside of Saturn? Because Saturn's a big ball of gas and fluid and stuff, and it's just rotating around. Why can't we use SKR to determine that? Saturn has a relatively weak radiation belt compared to like Jupiter or something. It's it's even weak compared to Earth. The densest part lies between Enceladus and the A ring. So Enceladus is at the E ring, and the A ring, that's the densest part of the radiation field around Saturn. So we're right there. We're right there. So if you want to measure radiation around Saturn, we're in a great spot to do it. It's much weaker than Jupiter, but it's still, the radiation from Saturn will still weather the moons. It'll still impact Enceladus and the other internal moons of Jupiter. Sorry, Saturn. How do you measure radiation? There's 3 basic ways to measure radiation. I call them Geiger, but they're basically gas-filled counters. There's scintillation counters, and then there's dosimeters, okay? A gas-filled counter, or what we call a Geiger counter or a Geiger-Muller counter, I don't know what you want to call it. Those, it's a tube full of gas with a glass top on it, and a radiation particle enters the tube, and it changes the voltage inside the tube, and this voltage measured, and boom, it can measure the radiation. It's small, simple, tested, very basic. You've everyone heard. I can't make the noise. That noise of radiation. That's the output you hear from a Geiger counter. And they can't differentiate low rate. They can't differentiate between the energy of the different particles, because it just measures the voltage across. It says, okay, radiation is in there. I don't know whether it's alpha, gamma, or whatever, but it just measures radiation. Okay, so that's how Geiger counters work. They can be very small. That's why I showed you this picture. They can be extremely small. This is like a circuit board, and it's on a circuit board. So Geiger counters can be very small. Scintillator or a scintillation counter. Basically, it converts radiation. You can Google it. A scintillator converts the radiation into photons, and then the photons are converted, the light signal, into electrical signal. So it goes radiation, photons, electrical signal. And then that electrical signal is measured, and that's how they measure the radiation. Now, they're inexpensive. They're kind of small, too. That's a small scintillator there. They can measure intensity and energy, and which is better than a Geiger counter, because it doesn't measure that. It just measures the intensity. It doesn't measure the energy. However, it requires complete darkness, which is why a lot of them there'll be a covering on it, like a foil covering, because it uses light. It uses photon. It's a light. The radiation creates light, and so if there's any stray light, it will impact how the scintillator works. And then a dosimeter. This is like the badges that people wear. That like if you work around radiation, you'll wear a dosimeter on a badge or something, and you turn it in every day. That's what a dosimeter is. They're very simple. It's the interaction of radiation with a specific material. So these dosimeters are made from different materials. You can use a dosimeter. Simple and common, used in the medical industry, space industry, stuff like that. Medical, where they, X-ray techs wear dosimeters, or if you're, radiation therapy people use dosimeters just to make sure they don't get exposed to too much radiation. They wear a dosimeter on them. They're specialized typically for certain types of radiation, and they only measure dose, like so much from when you started it till you ended it. It doesn't measure flux. It won't tell you, oh, at a certain time today you experience a lot of radiation. It just tells you how much radiation you measured from when you started to when you stopped. So that's a dosimeter. It measures dose, not flux. So those are the 3 basic types of radiation measurements. Magnetic field. It's a description of the magnetic influence of electric currents and magnetic materials. A magnetic field is a vector, and a vector, also the bad guy from Despicable Me, great movie. Magnitude and direction. I can't do vector. Oh yeah. So usually it's the magnetic field is given the symbol B with an arrow over it, because vectors have arrows over them, and they call it a B field, something like that. So if you hear someone say B field, that means magnetic field. It's produced by moving, like a magnetic field. You can produce one by moving an electric charge, or basically, if you have a permanent magnet, that's an electromagnet. A permanent magnet is from the intrinsic magnetic moments of elementary particles, like ferrous materials have magnetic properties to them. So the magnetosphere of Saturn is created by internally generated magnetic field. Saturn, they think it's got this metallic hydrogen, when you get down deep enough, it's a metallic hydrogen that's moving around. So moving metal, ionized, creates a magnetic field. That's what they think is going on at Saturn. It's the second largest of all the planets after Jupiter. filled with plasmas, mainly originating from Enceladus. Enceladus and Saturn have a really interesting relationship, magnetically field speaking, and electrically speaking. They have a really interesting relationship. And it was studied by Voyager and Cassini. So here's an image of the magnetosphere of Saturn, and the blue area is the plasmas, and here's E-ring is where Enceladus is. There's Dione, Rhea, Enceladus is inside there. So, all right. So the Saturn and Enceladus interaction. Cassini, when it flew by, it was measuring Saturn's magnetic field, and when it flew by Enceladus, it noticed that the magnetic field changed as it got by Enceladus. It changed a lot too. So scientists have determined that Saturn's plasma is being diverted away from Enceladus. Basically, Enceladus is changing Saturn's magnetic field is being changed around Enceladus. Very cool stuff. Okay, so there's your magnetic field lines, and as they get to Enceladus, they're changed, they're bent. Really interesting stuff. That leads to the Saturn Enceladus circuit. It's an electrical circuit that exists between them, not like with wires and stuff, but with ions that are constantly moving along these magnetic field lines. Basically, when Cassini flew by Saturn along the along the North Pole area, they discovered a presence of electric circuit that connects Saturn and Enceladus, a glowing patch of ultraviolet light near Saturn's North Pole, and a corresponding glowing ultraviolet part near Enceladus. They determined that there's an electrical connection between the two, where they pass ions. Ions, electrons are passed through this electrical connection because of the magnetic field lines. So jets of gas and icy grains that emanate from the South Pole, the tiger stripes of Enceladus, basically create this. It releases ions and stuff. Okay, so there's this electrical charge. And this electrical charge, this cell, and Enceladus itself is moving through the magnetic field of Saturn. So you have this electrically active thing moving through a magnetic field. So what that does, that creates another magnetic field, and then a circuit for the two of them to act on. It's really kind of neat stuff. It's a little bit more advanced than I'm getting into right now. If you want to do this for a science objective, you can get into it and jump into the the EM theory of it all. It's really kind of cool stuff. But so it basically sets up an electrical current system that links the moon and the planet. So there's electrical current. You can see it in this one too. There's a current that goes between Saturn and Enceladus along the magnetic field lines. Very interesting stuff. How do you measure magnetic field? I don't know. How do you measure it, Matt? So magnetic field magnetometers are used to measure magnetic field. It's one of those easy ones. Magnetometer. So and again, I said a magnetic field is a vector. You can measure just the scalar portion of the magnetic field, which just gives you a number, proton resistance, Overhauser, cesium, whatever. Or you can measure the magnitude and the direction of the magnetic field using rotating coil, Hall effect. Hall effect is the most common way to measure magnetic field lines on Earth. Magnetoresistance, flux gate, squid, or surf, etc. A flux gate magnetometer is the most common way to measure magnetic field on a spacecraft. So Hall effect is on Earth. Flux gate is used typically in space. Flux gate magnetometers, most popular on a spacecraft, they're light. This is a flux gate magnetometer actually. Look how big these wires are in this image. This is a very, very small thing. Okay. They're light, low power, robust, and simple. Easy to use, very simple operation. It's two coils. There's basically one coil that is activated with a coil of wire. It's like a solenoid, okay? They coil wire and they run current through it. And that creates a magnetic field. There's another coil that sits right next to it, and it just sits there and monitors it. So this magnetic field is created. Now furthermore, they alternate the magnetic field. So they have this magnetic field that's in this main coil, and it's going one way, then the other way, one way, then another way, one way, then another way. And then so this other coil is sitting there and it's doing nothing until there's a change in the initial magnetic field. When this thing enters a magnetic field, the magnetic field that's set up inside there changes. And any change in the magnetic field that is set up inside this main coil is felt by this other coil. This other coil feels changes in the magnetic field and in the magnetic field. So this other coil, it feels the voltage and the amperage of the change in the magnetic field, and it measures that, and it's calibrated, and they can measure magnetic field lines. It's kind of simple stuff. So one coil just sits there and it searches for the magnetic, just sits there and waits. It goes, oh, it changed, I felt the change, I felt it. So that's its job. So this is a picture of Earth with the magnetic field of Earth. They've mapped Earth a lot, you know. So it's all great. Magnetic field, magnetometers are awesome, right? The problem with magnetometers is they don't just measure the magnetic field that you want. They measure all magnetic fields. So if you've got it next to a processor or a computer, it's going to measure that too. If you've got it next to a spacecraft, it's going to measure that. If you got it next to, this computer or this television, it's going to measure that. So most spacecraft, when they have a magnetometer on board, they'll have it on the end of a long boom, like a 10-meter boom, so that it's far away from any interference. What they'll do is they'll usually have two of them. They'll have one magnetometer at the end of the boom and then another one at the base of the boom. And then if they're really paranoid, they have one in the middle too. So magnetometers are awesome, but they measure all magnetic fields. So there's isolation. You need to get it away so you don't measure the magnetic field of your stuff, of your processor, of your transmitter, or whatever. You want to make sure you're measuring the magnetic field of what you want to measure, not your own stuff. Issues with radiation and magnetic field, there's isolation, as I just talked about. The spacecraft or the lander or your probe, your processor will interfere with magnetic field measurements. Also radiation, the spacecraft is going to emit its own radiation because it's going to have a nuclear power source on board. Other obstacles can get in the way of these measurements as well. Time, location, again, you got to know where you are and what time it is, or have at least a synchronization, have all the watches synchronized so that the measurements make sense. You can't take a measurement and just say, it's 4, and you have to know where the measurement was taken and when it was taken for the measurement to be valuable. And then with the radiation stuff, there's a field of view requirement. If it's looking, if there's a field of view requirement, you got to be careful that it can actually see what it needs to see, that it's not blocked by something, that something's not in the way, basically. So that's all the science stuff explained. I know it's like this video's been 18 hours long so far. So what's next? Your team chooses your science objective. Typically, like I said, you start out with, what are you interested in? What planet or moon are you interested in? Start with the big stuff. Are we interested in Enceladus, Rhea, Down, Venus, Saturn? What are we interested in? Then you dial it down. What about that planet or moon interests you? You want to look at internal structure, temperature, what? What about that interests you? And then keep going down until you figure out, till your team decides on your science objective. Or if your teacher wants to help y'all choose that, then that's up to y'all. So research, once you find your science objective, okay, if you're looking at Venus, you start researching Venus, because Venus and Enceladus are really different. One's really hot, one's really cold. So once you find your science objective, research the environment associated with the science objective. So start looking at what Enceladus, what's the temperature there? What's the temperature of Rhea or Down or wherever we're going? Wherever your science objective is, start looking at that place. And then also, what your science objective is. If you're looking at seismic, or you're looking at heat flow, that's going to change that doesn't change your environment, but it changes what you need to know about the environment. How often, like for seismic events or for internal structure, how often do these quakes happen? But for heat flow, how hard is the surface? Can you get through it with the penetrator? What's the temperature? What temperatures do you expect to see? Stuff like that. So depending on what your science objective is, you need to know different information. And depending on where your science objective is, you need to know information. So once you find your science objective, start researching stuff like that. Start thinking about the instruments needed to satisfy your science objective. I've talked about a lot of instruments on this presentation so far. We'll give you more information on instruments, but this is already too long. This presentation is too long as it is, so we'll save it for another one. Start filling in the science traceability matrix. The science traceability matrix is on the next slide. It'll be in your book if I ever get you a book. So This is an example science traceability matrix. A science traceability matrix starts with your objective and then ends with your instrument. So it's a logical step by step. So our science objective is we want to determine the internal structure of Enceladus. Let's just say Enceladus. This is an example. This is an example, okay? We want to determine the internal structure of Enceladus. That's our objective. What are we actually measuring on Enceladus? We're not measuring internal structure. There's no such thing as an internal structurometer. We're actually measuring quakes and vibrations, okay? So what are the requirements on these measurements? We have to have at least 3 probes because we need to make a network, and it's at least 3. And we've chosen to stay on the surface for this one. We want a minimum of 1.4 days. That's because it takes 1.4 days for Enceladus to go around Saturn. And then we want to measure continuously during that 1.4 days, okay? Those are our requirements so far. This is an example. I've left some stuff out on this example just to make sure you don't cheat and use this. Okay, so, and then what are the instruments we're going to use? We're going to use an accelerometer to determine, we're going to use an accelerometer to measure these vibrations and quakes and stuff. So that's the science traceability matrix. It kind of walks you through it. Next is the instrument matrix. The instrument matrix takes each instrument and says, okay, what are the mass? How much does this instrument weigh? How much power does it require? How big is it physically? You know, stuff like that. That's the next matrix we're going to do after this. But start the science traceability matrix first. So that's the science. If you've watched the whole thing to this far, I salute you. You're a better person than I. I had to pause halfway through and take a break. Anyway, we will. If you have any questions, talk to me in class or email me or whatever. Ask your teachers. But we want to get these science things nailed down within the next couple of weeks. This is not something you want to have lingering throughout February. You want to get them done. You want to have all the science nailed down by mid-February at the latest. This is about it. So thank you very much for watching. And if you have any of your own science objectives, go for those too. But hey, good job. And we'll see you guys in class. Thanks. Bye.